All right. Hey, everyone. Good to see you again. So we are going to go ahead and continue with our discussion on ordinary differential equations. Like I said last time, it was, like I said just now on Zoom, that we're getting really strained on time. So we might not be able to cover everything I wanted to cover for boundary value problems, but at least we're going to nail initial value problems for a single equation and a system of equations. Today's lecture is going to be really exciting. Hope we cover everything in it. So initial value problems are going to be really important for your chemical engineering education because at least at the undergraduate level, we always assume well-mixed systems. And when you have well-mixed systems that evolve over time, that react over time, that's the recipe for an initial value problem. So I want you to know at least to have the tools that you can use to do ODEs. You're going to hit those in kinetics. And when you go and take kinetics with Professor Nigra or Magda, hey, you should know your ODE, okay? Don't say that you did not know those. All right. So last time we left off, we talked about ODE int. And the way I'm approaching this ODE stuff is opposite to what I've done previously in the lectures where we developed our own code and then learned at what Python does. This time we're doing it the other way around because it's easier to do it with Python. It gets you excited, you see results, and then that motivates you to study what's going on under the hood, under this ODE int. Now recall, last time with the problem, we did the lobster problem, we looked at SciPy's ODE int that takes at least these three arguments, a right-hand side, an initial condition, and a time domain. Remember, the strategy was to split the time into sub-intervals. So ODE int needs to take this time domain. This is just a lint space. You could create it equally spaced, unequally spaced, it's up to you. But generally, it's just easier to do an equally spaced time domain. The right-hand side is a Python routine that needs to look like this, right side phi t. It always assumes that the first argument is the dependent variable and the second argument is the independent variable. So be careful about how Python solves this equation. d phi by dt equal right-hand side of phi and t. So just put the arguments this way. Now inside the right-hand side, whatever there's phi, just put phi, and whatever there's t, there's just put t in there, okay? So this is the right-hand side. You just pass the name of the right-hand side, an initial condition, and time. So we're going to switch now back to Jupyter Notebooks. But before I get there, I'll remind you that we went ahead and played around with a couple of examples. We changed the the convective heat transfer coefficient for the liquid. So whether you're doing in air, water, or oil, we changed the temperature, the boiling temperature of the liquid, and we changed the temperature inside the oven. Remember, we were trying to find the fastest way to cook the lobster. Is it going to be in a lick because we needed to eat them as snacks, or substitute the lobster with eggplants, growing population eggplants or lobsters. So we need to find the fastest way to cook those. We looked at playing around with the parameters. Now, remember, every time we changed a parameter, we had to go to the right-hand side function, or we had to declare a global variable, which is a really bad idea, okay? But in the way we did it was every time we had to go and manipulate the right-hand side function. So we would change h over, for example, and maybe t infinity over here, and then also change the t infinity in this guy. So that's really bad practice. I mean, you could do it this way, but every time you want to change h and t infinities, it's going to be annoying. You're kind of hacking your way around this. There is a better way of doing this, and the better way is to allow the right-hand side function to take additional arguments. So the standard form of the right side function was right-hand side phi comma t, right? What if you also pass to the right-hand side function t infinity, h, other parameters, the area of the lobster, whatever you want, other parameters that might not be necessarily constant. And then you could do this from your routine, where the primary routine, that cell in the Jupyter Notebook that you're running everything from, you just call the right-hand side function and give it those additional arguments. Turns out that ODE int allows you to do that. and we can pass additional arguments to the right-hand side. So if your right-hand side, for example, looks like phi t a, B, C, or A, or A, B, or A, B, C, D, E, F, G, or 1,000 additional arguments over here. Doesn't matter. Doesn't need to be 3 arguments. What if your right-hand side, you want to pass hundreds of additional arguments that that you need to build your right-hand side? Okay, you can do this. You just simply define right-hand side like this. Always the first parameter is going to be the dependent variable. The second argument is going to be the independent variable. And then the remaining arguments are going to be your additional arguments for the right-hand side. Then the way you do this, you have to tell ODE int. Remember, ODE int, it calls the right-hand side internally all the time. And therefore, when ODE int calls the right-hand side, it needs to call it and pass it the arguments as well. And the way you do this, you simply add one additional parameter to ODE int that contains the arguments that you want to pass to the right-hand side. Whoops, show you this way. Over here. I keep messing that. Okay, one click. All right. So you see these, and they need to be matched in terms of order. So if you're passing h and t infinity over here, this needs to be h t infinity. If you swap t infinity a, they need to have the same meaning, okay, in the same order, right? So we're going to switch back now to our Lobster notebook and finish that off. And we're going to do this right now in the notebook, and so that it simplifies how we are attacking this problem. And then we'll switch to doing systems of ODEs. All right, so I'll see you on Zoom. All right, everyone. I am back on Zoom, and let me see if you can see the slide. Cannot see the slide, but if you open up your notebook with gaps, the one that we were working with last time, remember every time, okay, I'll give you a minute to pull that up. Remember, every time we wanted to change the heat transfer coefficient or T infinity, etc., we ended up having to go to right-hand side convection and change H and T infinity, and then also change the right-hand side for the radiation case, and then that was annoying. And it would have been much easier if we were able to change those parameters right here, where I have things highlighted over here. So that's what we're going to do next. So what I have here, and let me see, are those defined on your end, on your notebooks? Is this what you see in your notebook? If you go to the section pass params to the right-hand side,
yeah, we see that.
Okay, great. So what I've done here, I declared new right-hand side functions called RHS convection 1 and RHS radiation 1. But look at those. So those take still the dependent variable as the first argument, which we're calling t, and time for the second argument. But then for the convection, I need to pass heat transfer coefficient and T infinity. Okay, because I want to manipulate those. I want to switch the type of liquid or fluid we're cooking the lobster in. And I control that by changing the heat transfer coefficient and the boiling temperature of the fluid, okay? However, I keep the lobster surface area fixed. Could you pass the lobster properties? Of course. Just add more arguments over there, and then you can essentially be dealing with different sized lobsters, right? But we're going to assume now the lobsters are all the same size, and that's what we need to change H and T infinity for convection. For radiation, we can only control the oven temperature. Are you warming up? Are you baking at 350? Or are you broiling at like 550? Okay, so the only thing that we care about is T infinity for the radiation environment. Okay, so go ahead and execute those cells. So nothing really changes in how those functions are defined compared to what we did before, except that now they take this t infinity and h from the arguments that are passed to the right-hand side function. Okay?
Could you share it on Zoom?
Oh, I am so sorry. Thank you for, big mistake. My bad. I apologize, guys. I'm so sorry. I'm going to share on Zoom. Okay. So I have to repeat the entire conversation now, the entire discussion. Okay. So if you know, now it makes sense to you, right? Now that you're seeing it on Zoom, it makes more sense to you. So I defined two new functions here, RHS convection one and RHS radiation one. And notice how I'm passing two additional parameters here, H and T infinity for convection, okay, because I want to change the fluid in which we are boiling we are heating the lobster, and changing T infinity for the radiation. Now those come in as arguments. And what's the advantage of that is that I don't have to go and edit the right-hand side every time I want to change something. All I need to do is change it in the place where I'm calling those functions. Okay, so just to show you how easier this is going to be, how much easier this is going to be, just execute the cells for the right hand side, RHS convection 1 and RHS radiation 1, and then execute the cell after that where we import ODE int again, and then define our end time 20 minutes and create a linear space of 100 points for the time and domain. And then I think in your problem you have a T0 over here in your notebook. Okay, so now notice what happens here. Now here I'm declaring H, T infinity for the fluid, T infinity fluid, and T infinity for the oven. And now I call ODE in just like we did last time. For convection, I give it, for cooking it in the fluid, I give it the RHS convection, give it initial condition, give it time, but then I pass the additional arguments H and T infinity fluid. So what that does, it internally sends this H and T infinity fluid to the right-hand side convection and uses that in that function. Same thing for radiation. You call ODE int, give it right-hand side radiation 1, initial condition T0 time, and we need to pass it the argument T infinity oven. Okay, you got to put a comma over here, otherwise Python might bark at you. So just do that. Now, when you execute, you're going to get an answer. Okay, you're going to get a figure. Okay, so now let's say you just want to change H, go to air. H of air is very small. So let's do like maybe 10 for air, or I don't know, 50. In air, well, it takes a long time to reach the desired temperature. Okay, but you see how easy it is. We just change H over here and it automatically got picked up over there. Now you might say, oh, Professor Saad, I can declare this as a global variable. Don't do that. Because if I go and execute this before I execute the other cells, or execute the other cells before executing this, it's not gonna work. It's gonna bark at you. This is bad programming. Don't do it this way. Don't that the global variable way. Do it this way, okay? Because now what you can do, these right-hand sides, you can put them in other files, and just call them as libraries, essentially. So as you get more advanced in your programming. Anyway, now again, remember we're dealing with the physics. We are interested in solving the engineering problem, but we need these tools to allow us to solve the engineering problem. And now you can around with these numbers. So, these numbers are in Kelvin. For air has a very low heat transfer coefficient. Water is somewhere around maybe 150. And let's say, so water boils, I don't know, let's keep it at 350, and then the oven, let's broil the thing at 550K. Still, the oven is going to be faster. But then if you go to a cooking oil, you increase the heat transfer coefficient. That's like 300 maybe. And then it has a higher boiling temperature, 450. And so if you do that, then cooking the lobster in oil is going to be faster. You can cook it in like 2.5 minutes. So the x-axis over here is in minutes. Okay, so this is wrong, not seconds. Okay. Now you can reverse engineer this. You can say, I want to cook it in 1 minute. Okay, so then you would need maybe a fluid with a heat transfer coefficient, I don't know, 500, right? So you see, if you do 500, then you cook the lobster pretty much in about 1 minute. You reach what, 300, 400 degrees in about 1 minute. And then you would say, okay, to do this very quickly, we need to discover a cooking fluid that has this high heat transfer coefficient. All right? Okay. At the end of your notebook, so the next section is going to be using our own integrator. We'll worry about that later. But at the end of the notebook, I have an interactive thing. If you just go ahead and execute the cells, you're going to see something like this. And you can then play around with H and C and T infinity, and you get an update of the curve, okay? Like a user interface thing, okay? So it's up to you, play around with those. You're not responsible for this. This is kind of an extra thing. Some of you might be interested in copying this and adapting it to their own assignments or work. Good luck with that. But I'm not gonna help you debug the GUI. It took me. I needed help debugging it because it's so finicky. But feel free to just copy it and use it in your own homework, in your own work or etc. All right. I'm gonna switch back to the lecture now. I'm gonna switch back to Zoom to YouTube, and we will start the discussion on systems of ODEs. Okay. We still haven't understood what is. All right. Now that you're all convinced to use parameters, additional parameters in ODE, this is a superior way to using global variables and committing grave errors with that. We can wrap up initial value problems for a single equation. There is nothing preventing you now from solving a time-dependent ODE with an initial condition. You can apply, you can use this in your, if you're taking ODEs right now, go ahead and try it out with your math classes and see the solution that you get numerically, okay? You have a very powerful tool right now in your arsenal. All right, the next section is chapter or systems of ODEs. And clearly, since we are dealing with initial value problems, we're going to be focusing on systems of initial value ODEs, okay? And I'm going to use this chapter, this discussion, to also help you think about how you can create ordinary differential equations. Similar to the population example that we gave last time, we're going to take this up a notch, and I'm going to leverage the pandemic to drive home the example of the need for systems of ODEs, okay? There is a huge section, a huge literature in ordinary differential equations that is called compartment models for ODEs. And these are very simple and intuitive that I feel that if you learn them, you'll understand most of the ODEs that you're going to be encountered with, that you're going to encounter. And these compartment models, as the name designates, they essentially think of the thing you're studying as a compartment with things coming in and things leaving, and just simply do a balance of what's coming in and what's leaving, and you get your rate of change or the differential equation. To do that, we're gonna consider a department store. Pick your favorite department store. It's like no one's to department stores anymore, but now as we open up again, it's interesting to go to department stores. People are interested in seeing each other again. And so in a department store, there are people in the store. existing in the store at any time. There are shoppers, there are employees, people trying to sell you things, solicitors, whatever, these little kiosks, people calling you. If you go to the fashion place in Sandy, there's always someone, they have these like little kiosks, someone trying to sell you something like, I will fix your phone, I'll fix your glasses, a wristband, or anyway, I always like to chat with those people just to see what they're trying to sell. But anyway, at any point, there is a number of people in the department store. Okay, now let's designate this population of people this population in the store by the letter N. Okay, call that's the total number of people in the department store. Now the store has an entrance and has an exit, and the rate of change of the population inside the store. So now our store is our compartment, there's population in it. The rate of change of the population inside the store depends on how many people are entering the store and how many people are leaving the store. Makes sense, right? There's nothing too fancy about this statement. Okay, it's just full common sense. Okay. Now, if people are leaving the store, then we expect the rate of change of the population in the store to be negative, right? Because it's shrinking, it's going down, the population is going down. If you just take that population and people are leaving, we expect that rate of change to be negative, okay? In other words, this would look like this. dN by dt, rate of change of the population, is minus the rate of people going out. Now, clearly, there is a positive number, and that's going to be implicit assumption over here. And that's why you see the negative sign enforces that this is something leaving, clearly, because the number of people is a positive number. So you could have 0 people leaving, then the population doesn't change. But if you have 10 people leaving per second or per minute, then that is going to be a negative number. Okay. Now, like we talked about the lobster population early on, or paramecium, the larger the population in the store, the more people are likely to step outside, because you have more chance that people are gonna leave the store, right? And then you could argue that this rate of people leaving the store is actually proportional to the population in the store itself, right? So you write this as minus alpha times n. Okay, that's how you build these ODEs, right? Just makes sense. You could say minus alpha squared. Maybe those people are, in a rush to leave the store. But very likely what we observe in nature is that typically populations change proportional to their size. Okay, great. So that tells us about people leaving. Okay, that gives you the first anchor that when something is leaving the compartment, then it's a negative value. The rate of change is going to decrease, okay? Now let's take the other story, the opposite side. If people are entering the store, then we expect the population in the store to increase, right? Makes sense, right? So therefore, the rate of change needs to be a positive number. And because we are dealing with positive quantities, the number of people, you can't have negative number of people. You can have 0 people coming in, or 1 or 2 or 10, 15, right? So that means that the rate of inside the store, dN by dt, is the rate of number of people coming in. But you see, this is a positive quantity. And that tells you that dN by dt is increasing, so more people are coming in. Now, similarly, the more people that are outside, okay, the more likely that they're going to step into the store, okay? But the people outside are not N, they are a different population, because our compartment is the department store. But the people outside the store, they are a different population. Let's call that population I, stepping into the store. All right, so what that means now, the larger the number of people outside, the more likely they're going to step in. So that tells us that this Rn is a number proportional to the population that is outside of the store, this beta I, okay? Now that's important. Now, we not only have N, the population inside the store, we have the population outside the store. And we introduced a new variable over here, for which we're gonna need another differential equation. And I'll show you how we do that in a couple of slides, okay? But for now, what matters is that in general, if you consider any population or any compartment, this population could be a react or a number of cells in a biological system. Okay, so you could apply this to in kinetics, this is like a classic example in kinetics, as you are mixing hydrogen and oxygen, you're consuming those and you're making more H2O, right? So in general, the population of hydrogen, the population of oxygen, they're combining and then producing H2O. The population of H2O is increasing. So in general, for any population, any compartment, or any isolated thing that you think of that has in and out, in general, you can write the rate of change as something that's coming in minus something that's leaving. Now, the form of those things are going to depend on your system, and we're going to see that with an example with the pandemic. Okay, so bear on with me. This is very exciting to me, and I think it will help you understand how how easy it is to actually model an epidemic or a pandemic. There are differences, but call it what you want. The modeling strategy is very simple. It's based on this simple compartment model that I told you about. Okay, in a population where there is a disease being spread, there are three populations. You can think of more populations, but at least there are three populations. There's the population of susceptibles. Those are those of us who have not been sick yet, okay? And there's the population of those who are infected and are carrying the virus around, right? And there's the population of those who have already recovered, have gone with their lives. Now, the recovered can be susceptible again, but in general, let's say they're not susceptible again. Okay, you can build a model for the recovered to become susceptible again, but in general, we're just going to think that there's a population of susceptibles, and there's a population of infected, and there's a population of recovered. We assume that the recovered, that's it, they are not going to be infected again, they cannot be susceptible again. Okay, makes sense? All right. Now, we're going to call the susceptible with a variable name S, the infected with a variable name I, and the recovered with the variable name R. Okay. Now, clearly, only one way for a pandemic to progress, and if you have if you have a single infected person, and that is that the susceptibles are going to leave the susceptible category once they become infected. They're going to leave the susceptible category and move into the infected category. So the rate of change of susceptibles is going to be a negative value, right? Because you are decreasing the number of susceptibles. Once one of them becomes infected, okay, then they're going to leave the susceptible category. So we say ds by dt is minus R1, okay, and R is a positive number. And the larger susceptible population, the more likely that they are going to leave, they are going to become infected, because, it's easier to infect 1 million people than 3 people, right? You have more chance of interacting with them. But there's one little caveat over here. This ds by dt cannot be alpha s, okay? Because for a susceptible person to become infected, they need to interact with an infected person. So how can we model this with an ODE? This is the jump that I need you to make mentally, is simply take the product of S, the susceptible, by the infected. So every time they interact with each other, that's a product. So if you have 1 million people interacting with one infected person, there's one chance in 1 million, like for example, for one of them to be infected. But if there's 100 infected people, there's a higher chance of them to be infected. So the way we model this, we simply keep the coefficient, a constant coefficient, times I times S. So we multiply the susceptible with the infected, okay? Once the susceptible interacts with an infected, then they're going to become infected, okay? And that essentially tells you the rate of change of the susceptible moving from susceptible to infected. Now, they are scaled by a coefficient beta. That's the rate of infection. So that essentially measures how fast a virus spread. So I might interact with an infected person, or 1 million people might interact with one infected person, but it's not all of them that are going to infect it. Only a very small fraction of those are going to infect it, and that's going to be scaled by beta, okay, by this parameter. And that tells you how infectious a virus is. So I don't know the beta for the SARS-CoV-2 virus that causes COVID-19, but typical numbers that I tried to model with what we've seen with the pandemic is about 0.15, but you can play with this number, okay? Again, we're trying to shed insight into how a pandemic spreads. Okay, so great. Now we're done with the susceptibles. The susceptibles are only losing, right? There's nothing coming in, okay, unless now you can assume that people are flying from other states into the susceptibles. Let's say we shut down everything. No one is coming in. We have no new susceptibles, okay? So the only way for susceptibles to go is to be depleted, all right? So we get minus beta IS, and they will only move out of being susceptible, interact with an infected person. Okay, so now we go to infected. And in general, like we said, for any compartment ODE, for any ODE like that, it's going to be whatever is coming in minus whatever is leaving. Now we know what's coming in, right? It's these susceptibles, beta IS, are leaving the susceptible, but where are they going? They're going to the infected. So we know the input rate of the infected population. It's beta times IS. They leave, minus beta IS leaves the susceptible, but beta IS comes into the infected, right? That's the rate of people coming into the infected category, okay? Now, how many are leaving from the infected? Are there any people leaving the infected? Absolutely, because you get sick, 10 days, 14 days, 30 days, 5 days, you're gonna recover, okay? So we do have a rate of people leaving the infected category, and that is gonna be the minus out over here. And if we assume that the infected recover at a certain rate, gamma times I, to become recovered, then that's how many people are leaving the infected category. They're not interacting with anyone. They're just infected, they got sick, and they're just sitting there to be recovered. Turns out that gamma in this model is the inverse of the recovery time. So for COVID, it's 1/14 days, okay? That's an actual value for gamma, okay? Now, finally, we have the recovered. What do we got for recovered? There's no leaving recovered, only people coming into recovered. So dr by dt, d recovered by dt, is simply gamma I. So minus gamma I are leaving the infected, but gamma I are going into the recovered. Okay. If you're not excited about this, I want you to be excited. We just developed a model for an epidemic, for a standard epidemic. And it's as easy as I described it. You just take the 3 compartments, have some thought about it, and say, okay, however, how many are leaving? How many are coming in? There are some coefficients. Have the boldness to make assumptions, okay? And we're gonna play around with this model together in Python, but that's a system of equations. We have equation for the susceptibles. ds by dt is minus beta is, di by dt is beta is minus gamma I, and dr by dt is gamma I. 3 equations are dr dt, di dt, ds dt, and 3 unknowns, s, I, and r. The parameters are constant, beta, alpha, and gamma. You can play around with those to understand what a pandemic looks like. But if you solve this problem, and I'm gonna give you a chance to play around with the numbers, this is my solution with some parameters that I chose, okay? And this is what I'm plotting here in terms of percentages. So what I did, I divided the coefficients by everything by n, so that I normalize, I look at a percentage of the population. So the y-axis is the percentage of the population. Initially, my initial condition for the population was, 100% of the population. So the blue is susceptible, the blue is susceptible, red is infected, green is recovered. Okay, so initially, most of the population, 99.9% of the population is susceptible, and we only had one infected person over here, one infected person. Now, as the infected person interacts with the susceptible, and as they recover as well, the infected person, then you see the population of susceptibles be depleted, okay? But the population of the infected starts growing. Now, eventually, so the infected is feeding on the susceptible, but the recovered is feeding on the infected because the infected people are recovering. okay? And so you see how we peak with the red curve, and then as the red curve starts consuming more of the susceptible population, okay, it doesn't consume it all in one shot, it takes time, then you have more people recovered and you see this balance, okay? So you see up to 60% in this model, up to 60% of the population peak got infected and it started dwindling down, and they recovered, they continue recovering until the entire population is fully recovered. What do we mean by flatten the curve? Is asking the question, what is an acceptable peak? How much can our hospitals handle? 60%? 10%? As far as I know, about 30% of the population is a decent number that hospitals can accommodate. That's at least what we see with the emergency room during the flu season. So the question is, how can we manipulate? Well, the question is, can we manipulate this? I'll show you later how we can manipulate this. But you cannot control how infectious a virus is. So the beta, the rate of infection, is not controlled. What you can control is separating the susceptible from the infected to effectively try to reduce the effect of this beta. Okay? Now, so these are three equations, three unknowns. Next, I want to show you how we solve this in Python. We take these three equations and just simply write them as a vector. So d by dt, put them in an array, SIR, okay? And their corresponding right-hand sides. They're just three equations, three unknowns. And describe this simply as d vector phi by dt is a vector of right-hand side of phi, all of the vector of unknowns, comma t, okay? To solve this, we will use SciPy's ODE, the same thing that we used for a single equation. Turns out that SciPy's ODE int solves not only a single equation, it also solves a system of equations, okay? And it takes the following form. So if we assume it solves a system of ODEs of this form, d phi by dt equal right-hand side of phi t, where phi is a vector of the unknown. So this could be susceptible, infected, recovered, killed, or whatever you want, socially distant, etc. And each one of those ODEs has a corresponding right-hand side. Okay, RHS0 for phi 0, RHS1 for the second ODE, RHS3 for the fourth ODE, etc. Okay, and so on and so forth. But this is the form that this solves. And each of those has an initial condition, okay, also described by phi 0 at t0 and phi 1 at t1, at t0, and so on and so forth. In Python, you just use the same formula, ODE int, except now the right-hand side, instead of it being a single value that is returned from your function, your right-hand side needs to return a vector of right-hand sides. The right-hand side of the first ODE, the right-hand side of the second ODE, the right-hand side of the third ODE. You see in Python how easy it is. Just put them in brackets, return them as a vector. But you have to put them in the order you intend to solve them, okay? Now, phi 0 is a vector of initial conditions. So you put them in bracket, you put your initial conditions for each equation. T is the time array sequence, okay, that we used for the single equation. So for example, for the epidemic model that we just solved, it's called the SIR model, susceptible, infected, recovered. What you would do is, in your right-hand side function, you call that function, call it SIR right-hand side, and in it you compute the right-hand side of the first equation, the second equation, the third equation, given phi and t, okay? And then you return those right-hand sides as a vector like this, okay? Same thing for phi 0, the vector of initial conditions. Those are just values, really, just scalar values, S0, I0, and R0, and t is your lens space, okay? Now, one more note I want to give you about what ODE int returns in the case you have more than one ODE. So when you have an ODE, the solution, the answer that ODE int gave us, the return value, was simply a vector of the dependent variable at t0, t1, t2, etc., tn, right? So for the lobster, it was temperature at the initial time, temperature after 1 second, temperature after 2 seconds, and so on to the end. Over here, the answer is going to return an array of arrays, okay? It's going to return a matrix, essentially, where in the first column, you have the solution, the entire solution for the first variable. In the second column, you have the entire solution for the second variable, and so on and so forth. So you see phi0 is the first variable, and in the first column, you have phi0 at t0, phi0 at t1, all the way to phi0 at tn. And then this is what you want to plot, right? When you want to plot phi0 versus time, this is what you want to plot, okay? And the way you do this now is, and this is the recipe in Python, is to kind of untangle all of this complexity. You say, okay, I want this first column. So the way I do it, I take solution, I put the semicolon, so that gives me all of the rows over here, and column 0. So that gives me this first column over here, indexed at 0. Phi1, which is the set dependent variable, is also solution, semicolon, comma, and 1. So that gives you this second column over here. Okay, all of this has been mostly pre-programmed for you in Python. And again, if the side has other arguments, you can do the same thing. You can pass those arguments into ODE in, just like we discussed previously. Now, for the fun part, let's go ahead and download the system of equations, SIR epidemic, SIR epidemic model with gaps. Go ahead and download that from your canvas, and let's work on this together, play around with the numbers, and see for yourself how an epidemic can spread, okay? All right, everyone, I am back on Zoom. Go ahead and download the SIR epidemic with gaps. SIR epidemic example with gaps. Let me see, do I have the one with gaps? Opened up over here. SIR example with gaps. Okay. All right, so I'm gonna share the screen with you. Thank you for reminding me. Okay. So now you can follow me on Zoom. This is all being recorded on YouTube. Let me see if I can change my camera. Okay. So now with this pandemic example, I have the equations typeset over here. Go ahead and execute the first cell. Do you have the notebook in front of you? Okay. All right. And these are the equations. This is all we need to fill in the gaps. So this is a notebook with gaps. Okay. Now, for this whole thing, we're going to have a single right-hand side. Okay. That returns a vector of right-hand sides. And we're going to solve these equations in this exact order: ds dt, di dt, and dr dt. So our right-hand sides are going to be, the first right-hand side is going to be minus beta is, the second right-hand side is going to be beta is minus gamma I, and the third right-hand side is going to be gamma I. So what I did here is I defined RHS SIR, okay, for the right-hand side of this system of equations. The first argument is always going to be phi, and the second argument is going to be time. Now this phi over here is the vector of solutions in this case, right? It's going to be phi0, phi1, and phi2. Or in our case, it's going to be S, I, and R, because that's how we're assuming we're solving them, okay? So notice here the comment: phi is the vector of dependent variables containing the three dependent variables S, I, R. So we can immediately assume that's by construction, because that's how we are intending of building our system of equations. Okay, now I have a question mark over here for you, because I want to pass some arguments for the right-hand side. Okay, some additional arguments for the right-hand side. So do you want to help me fill in, what do we need here for the question mark? I want to pass some arguments to this right-hand side. What do I need to fulfill this right-hand side?
Would it be beta and gamma?
Yes, thank you. Beta, gamma. Call them beta and gamma, okay? Or gamma, beta, whichever order, but stick to that order when you send in information from the ODE int. Okay, great. All right, so now let's hop inside the function. Now we assume we have access to all the dependent variables, SIR, time, beta, and gamma. Okay, so now I need to grab, so my right-hand side consists of minus beta IS, and then beta IS minus gamma I and gamma I. So I need IS, I need S, I, and R. Maybe I don't need R actually. Okay, so how do I do this? What is S over here? It's simply phi, right? So that's for simplicity. I'm going to designate by S, but phi 0 as S. What about I? Phi 1 and phi 2 is R. Because that's how I structured that's how I intend to solve the system, as SIR, the way I described it here in the equations. Now simply, my first right-hand side is for the first equation is minus beta SI, and you see here beta over n. That's a little, okay, never mind this, just put n over here. Like there are multiple ways of solving this, whether you put a fixed population or not, you want to plot it in terms of percentages or not. Let me see. Yeah, let's do it in terms of percentages. So just put n as an argument over here and solve beta over n, okay? That's all you need to change. Now you see here in this ds by dt, that's the first right-hand side. It's minus beta over n times s times I. di by dt is the second right-hand side. It's beta si minus gamma I. And dr by dt is gamma I. Now this right-hand side needs to return, this right-hand side function needs to return these three right-hand sides. So what do I put here? Now remember, this is going to dictate the order in which I'm solving these equations. And what is the order we decided on? Abby, you were saying you were muted.
Oh, I was thinking, is it SIR? Because that's the order that we decided.
But that's right. But are we returning S or the right-hand side for S, the right-hand side of R, and the right-hand side?
Right.
So
for S, and then.
So what do I put? What was my definition of the right-hand side for S? I called it ds dt. Right?
Oh. Yes.
Or you can call it RHSS, RHSI, and RHSR, whatever you want. But you have to return them in this order: RHSS, RHSR, I, and RHSR. Now, when you do this, then ODE int thinks the first equation has RHSS, the second equation has RHSI, and the third equation has RHSR. And therefore, that's why we say we're solving SIR in that order. Okay? Generally, what I'm describing here, you can just replicate over and over again and extend it, okay? And honestly, that's going to be the best way for you for this to sink in your mind. Okay? All right. So I defined the right-hand side for SIR. Now I'm going to go and try to solve this. So I'm going to start with a population, let's say 3,000. And with I need initial conditions. Initially, my number of infected people is going to be 10. So 10 sick individuals. My initial number of recovered people is going to be 0. And then that leaves me with susceptibles as n minus I0, right? So it's the total population minus those infected. Correct? It's 3,000 minus 10. Those are the susceptibles, right? Then I define my beta as 0.6. And gamma, let's say 1 over 20. I don't know what numbers you have on your notebook, maybe 1 over 14. And then my end time is going to be 100. Now, we didn't specify the unit for time over here, okay? But that can be manipulated by those beta and alpha. So you could assume it's days or years. It doesn't matter. It makes sense that it's actually days over here, okay? Because we're going to choose our parameters, alpha, beta, gamma, in such a way that such that the units work as if they are in days. Everything is in days, okay? So just t end is 100. Our units are days. Then we declare our t end. Okay, I want to do 100 days. So I put here int t end. Is this what you have in your notebook? Okay. Now I still need to declare my initial condition vector, which is going to be, I call it, let's call it phi0 instead of y0. It's going to be, again, in the order we intend, S0, I0, R0, okay? So you also have to change here phi0. Okay, now it's time to call ODE int. All right, so what are we going to put here? The first argument is always the vector of right-hand sides, or the function, the routine that does the right-hand side. What is that routine?
RHS, sir.
RHS, sir. Good. Phi0 is the vector of initial conditions. T, we declared that as time. What about the arguments? What does the right-hand side take? What are the additional arguments that the right-hand side takes?
So is it beta, gamma, and n?
Yeah, thanks, James. Okay, so we do beta, gamma, and n. Okay.
Professor, quick question
Yes.
on that.
Yes, Braden.
Do we have to have the \beta, the \gamma in our argument, or do we just spell them out as we did up in the right-hand side?
It depends
or would it matter?
No, it matters a big deal. It does matter a big deal. Because what you're passing here, you're passing these values, right? So you could call it B and H, or B and, Ga, okay? Then what do? You have to pass B and Ga, because that's what you mean by beta and gamma. In the mathematical model, in your code, you called beta B and Ga, and gamma Ga. You could have called it my beta and my gamma, whatever you want. It's just the name of a variable, but you have to make sure what your intent is. Over here in the first argument, your intent is to pass beta, the value of beta. So called, this needs to be my beta, and this needs to be my gamma. This is very important. You could call them beta and gamma. Beta and gamma. It's up to you. Okay? Inside the function itself, Braden, and you should know this by now, these are just placeholders. Their names, phi, t, beta, gamma, n, is only relevant inside the function. That's why I'm scared of global variables, because you might overwrite what you are using inside a function, okay? But inside the function, as far as the function is concerned, you're getting in slot, you're getting something, a number, you designate that number by beta, and then you use it accordingly. But what you're passing here is just a slot. In the first, in this slot, you're gonna pass this variable, this whatever you declared here. Okay, you're gonna pass this value, 0.6. In the second slot, you're gonna pass another number. That's what matters. Okay? Does this clarify?
Yes, thank you.
Okay, gamma. I'm gonna switch back to beta and then gamma. Okay. All right, so now we solved the system. How do we untangle S, I, and R from the solution? Now, if you run this, you're gonna get, okay, so let me run this. Let's see if it runs. I'm gonna run this, it ran, okay? Now, if I print solve, it's gonna be a nasty, just a bunch of numbers, right? Just a bunch of numbers, okay? So how do we untangle this? Remember that last slide where I told you the return value for ODE int when you're solving a system of equations is a matrix. In the first column, you have the first variable. In the second column, you have the answer for the second variable, and so on. So what I'm going to do is simply call sol, do the semicolon 0. That's me. The first column in that array contains S, the second column contains I, and the third column contains R. Okay? And now I can go ahead and plot. So just go ahead and plot this, and this is what you get. Abby is happy because this is the answer she got, right? Now, notice I divided S by N and I by N, R bar N to normalize things a little bit. You can remove that to get absolute numbers, but you got to adjust your limits, your X and Y limits, okay, so that you're able to see. You have 3,000 initially in the population, and then you have 10 infected, and it goes up and down. Okay, so now that you understand the math and the computing, now we can think about the physics. Okay, what if you had a longer recovery rate, a shorter recovery period? Let's say 4 days. Let's change gamma. Gamma controls that recovery, right? If you remember the pandemic, the model, the rate of people leaving the infected was gamma I, right? Was gamma controlled how many people are being recovered, okay? Or the rate of recovery, sorry, the rate of recovery. And so if we change gamma, so if we were dealing with a disease that had a very short recovery, what's going to happen? So let's change that to 1/4, let's say, okay, and run it. Look at that. The peak went down significantly. The red peak went down significantly. Why? Because people have a smaller chance of infecting others because their recovery is shorter, right? The recovery is shorter. Now let's take the other extreme. What if, you know, it took them like 50 days to recover? Look at that. Those infected, takes them a long time to recover. They're still circulating in the population, infecting everyone. Now, maybe one of you, and I'm going to propose to you, maybe one of you comes up with an improved model and says, okay, what if we isolate the infected? What if you add a compartment and call, you know, quarantined? Can you develop a model? I think you can. When a person gets infected, some of them move to a quarantined. Then what would happen? That we can bring down, that's how we can manipulate the pandemic, okay? Okay, so let's see now, let's go back to 14 days. Let's look at the infection rate. So beta controls the movement from susceptible to infected. So if you interact with an infected person, what is your likelihood of getting infected? Okay, that's beta, that's parameter beta. Let's think in everything you do in your, and even in your life, think of both extremes. What would happen at a very small number or a very large number? Okay, let's say you're thinking about saving for college. What would happen if I save no money, or I save a lot of money, right? Excuse me. Or, you know, eating ice cream, or dealing with specific engineering systems. There's usually a parameter or two that you can control to understand your system, okay? So the extreme. So what would happen when beta is very small? So 0.01, for example. Very unlikely to be infected, right? It's going to happen really nothing. It's barely a pandemic, right? It's barely infecting people because it's a non-infectious. It's like saying, you know, like heart disease, it's non-infectious. Doesn't, you know, you meet someone with heart disease, you're not going to have heart disease, right? So But what if it's very infectious, like 0.99? Okay, look at that. The 10 people infect everyone very quickly because it's very infectious. And then you can see how you can play around with all of those quantities, right? To understand how pandemics are behaving. Okay. Now, at the bottom, I have an interactive simulation for you, okay, where you can just move some knobs around, okay, and see how the pandemic behaves, okay. Let's say, so I did change something over here. Did I change something? LT, hold on. And, okay. So over here, the knobs, you have a bunch of knobs that you can control you can look at how the pandemic is moving. So I want you to change. So over here, here's what you do. Put S over N over here, I over N, and R over N. And when you do that, okay, still not working as I expected. Wait, something is off over here. 1 second. See, I changed the arguments over here. Okay, sorry. So I had a typo in the interactive simulation. See, Braden, I had the arguments incorrectly placed. I had N, beta, and gamma rather than beta, gamma, N, which is how we designed the right-hand side. Okay, so just fix this over here. Say arguments is beta, gamma, and N, right? Because that's how we designed our right-hand side. We intended to put beta first, gamma second, and N last. And then when you do, you get this interactive simulation where you can over here just play around with the infection rate, the recovery time, long recovery, etc. You can change the simulation time, however many months this is gonna run, okay, 4 months, okay? And you can play around with that as you please, okay?
Quick question.
Yeah.
Is the recovery days more of like how many days they're still infectious?
The gamma, you mean?
Yeah.
Yes, how many days they are infectious since they
Okay.
get sick to recovery. Now, I'm not an epidemiologist, but from a mathematical or engineering perspective, this is just a knob. Okay, and those knobs typically in actual models, as far as I know from the literature, they update those knobs pretty much every day based on what they observe. But the model is the same, minus beta is. It's not more complicated than that. Okay? It's pretty cool, right? If someone thinks this is not cool, tell me right now. Tell me if you're not excited about this, tell me you're not excited and we'll work on making it more exciting. I mean, this should be exciting, right? It's so cool. You're in your first, second year chemical engineering, and now you know how to develop a model for pandemics. And the same thing applies for kinetics, okay, for populations, for other things, the same methodology, okay? All right, so I'm gonna switch back to YouTube and then show you now how I developed a model with social distancing to essentially, not take either extreme, shut down everything and, increase the rates of suicide and alcoholism and all sorts of depression versus complete opening up and everyone dies, right? So in my opinion, science can help us find a middle ground where we can, intuitively, the way I would think about it is say, well, our goal is to flatten the curve, not to make it zero. Our goal is to say you can handle 20% of the population in hospital beds, right? That's always been the issue, right? Because people are going to get sick. It's immature to think that no one is going to be affected by a pandemic. It's like driving a car, flying a plane. There's risk in everything, right? But how much risk are we willing to take? If our hospital capacity requires 20% of the population, then why not do the following? Hey, let's open up and keep measuring our infection rates. And then once we start hitting some peak, we shut down. Okay? Shutting down has been shown to bring down the curve. So we bring it down, but as we bring it down, then as we feel comfortable again, we open up. Okay? And then as it climbs up again, we close down. And so that was my thinking. And that's what I ended up doing last year actually in this class. And I'll show you some of the results that I had and a link to play around with that model. Okay? I'm going to switch back to YouTube and we'll talk over there. Okay? All right, so I hope you were as excited as I am about developing an ODE model for epidemics. What I'm going to show you next is my vision or my interpretation of how we can flatten the curve. And like I said just previously, our goal should not be to have zero illness. If you are at risk, definitely prevent yourself, stay at home. You should be supported in any way. Like if you have an autoimmune disease or you are at high risk, then that's should be your choice to be to stay at home if you want, and have your groceries delivered. We did that. We had an at-risk person at home with a new baby, etc. So we stayed at home, we stayed put, we ordered deliveries, etc. But in general, as a society, the meaning of flattening the curve was to say how much hospital capacity can we handle so that we can give the best chance at those who were willing to take risk and get ill, to give them the best chance at surviving this. And, rather than hitting 60% peak capacity, we can't handle that in our hospital. What is our peak capacity? So I thought of extending the model, the SIR model, by adding one additional compartment and call that the socially distanced. Okay, D stands for being socially distant. So now I'm going to assume that a population consists of people who are distanced or who are, they stay quarantined. I don't want to say quarantined because they're not ill, but people like, my family early on, we stayed home. We didn't go out. We didn't move into the susceptible category. Okay, so this population is split between distanced and susceptible. Okay, and there is a two-way communication. Sometimes, we ended up wanting to take the kids out to the park, for example. So that put us in the susceptible category. But some people who were in the susceptible decided, now their grandmother came in to live with them, so they decided to be socially distant. So there is constant movement between distanced and susceptible, and we call that coefficient, we're going to call that delta 1 and delta 2. So delta 1 goes from distant to susceptible, and then delta 1 susceptible to distance, and delta 2 distance to susceptible. And then the susceptibles have, the standard SIR model. They go to infect and then infected to recovered. And now that we can develop the equations just like we did before. So from the susceptible, there is outflow from the susceptible, beta IS, but there is also inflow into the susceptible from the distance. That's delta 2 times D. And there's outflow from the susceptible to the distance. That's delta 1S. Okay, so the susceptibles, they move out in two categories. They move out to be infected, and they move out to be distanced. Distance, they are going to move out either to the susceptible, and whoever is going to come in from susceptible to distance. So you get, for the distance, you get delta 1S for everyone coming from susceptible. So it's increasing the number of distance. And however many are leaving from the distance to be susceptible, that's delta 2D. And then the rest is the same. D infected by DT is beta SI minus gamma, just like the previous model. So what I did here is just a simple, I added one compartment, okay? And I defined two coefficients for that compartment, okay? And let's see what happens. So now I have 4 equations and 4 unknowns, all right? So the first set of results, what I'm going to show you, I'm going to fix beta and gamma. Beta is the infection rate, say 0.5 infection probability. It really doesn't matter because I'm looking at the sensitivity of the social distancing. And gamma is 1/14. Okay, so this first plot, I am gonna, there is a fixed outflow of socially distanced to susceptible and susceptible to distanced. And I'm gonna play around with those numbers, the number for distance and susceptible, okay? So those deltas, those coefficients. And then I'm gonna plot in the curves. In the black, you see the susceptible population. Green is recovered, red is infected, and sorry, the black is the distanced population, okay? So with these numbers, what I'm showing here is that initially a population is susceptible, but then we increase social distancing, okay? And now compared to the previous case, the peak was at 60%. So you could see that the distancing does actually have an impact, okay? But then as we move on, the more people from the distance they go back to susceptible, because as the infection rates are going down, there's a balance that is reached. And then over here, I define a vaccine where everyone becomes recovered. So don't worry about that. That's a little trick I did with the code. But then if you play around with delta one, if you fix delta one, that's the movement from the distance into the susceptible. So more and more people are becoming, sorry, for fixed delta one movement, sorry, it's from susceptible into distance. Okay, so more people are being distanced. This is a typo here. So if we fix delta one and increase delta two, which is more social distancing, it clearly flattens the curve. So this is one value for delta 2, 0.02, and then 0.03, and then 0.04. You see there's more people being distanced, and you see how we flatten the curve. We bring it from 25% maximum capacity to 13% to 5.4%, okay? Now, clearly, if ever is socially distanced, the curve is gonna be at zero. The red curve is gonna be at zero. Okay, but it doesn't have to be like that. Like I said, and I'm gonna try to, I don't wanna rush through this. I have 5 minutes, but I think I can cover this. What if we don't do this? What if we do it smartly? What if we say, okay, we are willing to accept once the infection rates are at 10%, we are going to start social distancing, very high social distancing. And when the infection rate goes down to 1%, then we are going to relax things. So what I did, I defined my coefficients for however many people going from distancing to susceptible and vice versa as a function of how many people are infected. So if the number of infected is greater than a certain value, let's say 10% for example, then I'm going to increase social distancing. But when the rate of infection, the number of infected is less than a certain value, let's say 1% of the population, then I'm going to open things up again. And let's see what happens, okay? So now this delta 2 and delta 1, the value here, so if we hit a number smaller than 1%, let's say, or a number larger than 1%, I can play with this C2 and C1. That tells me how much social distancing I need to make or not, okay? So this is what happens. It's really cool, all right? So initially, we are in the susceptible and people are being infected. Okay, once we hit a certain number, bam, we increase social distancing. Okay, notice we start bringing down the curve. But then when the red curve reaches 1% in this case, then we're gonna open up again. So more people become susceptible, less people become socially distanced. So the black line decreases, less social distancing, more opening up. And clearly, as we open up, the infection curve is going to pick up again. And then what do? We switch it back again, and then we switch it back. And so we get this kind of wave that shrinks. And it doesn't have to be full social distancing. We can do this smartly. And instead of, shutting down everything, maybe we throttle it based on what we're seeing. And I bet everyone's going to be happy with that decision. Neither of those extremes, right? And you can start playing around with those numbers, with how much distancing you're willing to take. Okay, you see here, does our state of Utah can it handle 10%? Great, then we keep it here. Can we handle 15%? Then yeah, maybe, we can do it here. Now remember, peak infection, we're not counting those who actually were killed by the virus. What we're saying is we can handle any illness, any complications, we're going to give them the best therapeutics and the best scans, ventilators, hospital bed, so that they recover from the illness, right? So, you know, it tends to be like a good balance between everyone. And I keep changing the numbers over here, etc. And then I show what I'm here is my optimum design is you know, with certain manipulation of the numbers, if you do your social distancing like this very smoothly, okay, so use social distance initially and start opening up gradually. Like, you know, we first open up, I don't know, you do odd, even numbers for cars, or, you know, districts, you open up different businesses gradually, then you can control this peak, which is, I want it to be at 10. Anyway, so if you want to play around with this, there's an app that I built and I put it online. You can go and play around with the numbers and see the social distancing and all of that. And my challenge to you, if you want, develop your own model. Take the SIR or the CERD that I developed with here, or whatever you can think of, and maybe come up with your own model. Maybe think of, you know, what if we quarantine the infected? Okay, or what if we want to track those who have been killed by the virus? Okay, what if we want to track hospitalization rates? Okay, go and add a compartment and come up with a model. And if you send it to me, actually last year I had a student develop his own model for that, and I told him not to do homework, the last homework. Okay, he got 100% on the last homework. So, you know, do something like this. I might reward you with a cool thing. Okay, but your model has to be legitimate, and I need to see some plots, right? So you got to use the ODE int, etc. All right, I'm gonna see you on Zoom, and I'll tell you bye-bye on Zoom. All right, right on time. I got through this. Last year we breezed through this very quickly. I don't think many of the students appreciated it, but hope you do. I hope this was fun for you. So at the expense of the life hack of the day, I think, you know, spending time on this was worth it. Yeah. Any comments? I'm gonna hang out here a little bit, and then we have office hours at 3:30 if you want to come over and talk. Was this useful? Yeah. I hope it was exciting.
You delivered on the promise to make ODEs exciting. So
that's great. Thank you so much, Sarah. That means a lot.
thank you. Bye.
All right.
Thank you. See you.
Bye-bye. See you later. Bye. Bye.
So I would have just some questions actually about